So our next speaker is Kees, a professor from LSU. Although I looked and it looks like you did a master's at UNC, is that right?
Yep, master's and PhD at UNC.
Cool. So lots of Chapel Hill representation here today. But he's going to talk to us about his CutFEM methods. So thanks for joining us, and please take it away.
Thanks, Toby. And thanks to Matt and all the PETSc folks for inviting me. I'm like Boyce, I'm a longtime PETSc user. I went to one of the first PETSc tutorials at a SCIFEM geosciences meeting in San Antonio, I think, in the 90s. So anyway, I've been using PETSc ever since. It's always been a central part of any tool I've been writing. It's been there helping me with the parallelism and the solvers. So I'm going to talk about multi-phase flows really in the civil and environmental applications realm. Let's see. And unfortunately, I just bought a new Mac, and it's really throwing me for some loops. So I've cut out all of my nice, well, I don't have any animations as fancy as the ones you just saw, but I have some that are entertaining. First of all, acknowledge a bunch of different people. So I'm working with a bunch of different folks at LSU that are working on coastal ecosystems. So we're looking at, and I'll show some examples, but sort of, I've also been able to work with some mathematicians, to help design some of the numerical schemes. And so this is really over a 10-year effort, so it predates my time at LSU. But LSU has been a great place for me to really get into some of the important applications of these approaches. So I've got a map here of Louisiana. So there we are, and then zooming in, and then zooming in further. Those are two deltas in the Atchafalaya Basin. So one's called Wax Lake Outlet, and I forget what the other one's called, but they're both active deltas, so they're being formed, and they're being formed because Congress passed a law a long time ago that said 30% of the water and sediment in the combined Mississippi Red River Basin would go down the Atchafalaya. 70% will go down the Mississippi, and that was to keep the Mississippi what it is today. It was meandering over and about to head down the Atchafalaya, and so that's sort of a law that was made that affects, two entire river basins. And so what's happening in the Atchafalaya is that it's getting plenty of fresh water and sediment, and so it's actually building land and building deltas. And we can kind of understand those processes qualitatively, but just like in every other branch of science, we'd like to be able to reproduce them quantitatively from, sound principles, if not first principles. Okay, so a lot of what I'm trying to do is build up a multi-scale framework for simulating large-scale landscape processes. And a process like that is water interacting with sediment and soil, but that's also interacting with vegetation. So vegetation plays an important role. So we're trying to get all of those couplings together. So it is a fluid structure interaction problem, although the structures here, are less, the elasticity of them or the mechanical nature of them is less important. It's their complexity and how they interact with the fluids. So ultimately, we'd like to be able to get to the point where we can, do evolution of these systems, and we can understand how human engineering affects them, so that we can, in some cases, undo the damage that we've done. In other cases, maybe we can improve the situation. So in Louisiana right now, you might have heard of these sediment diversions, which are an attempt to sort of recover some of the natural processes that we have shut off by building levees and other types of flood control structures. So we can, while the river would naturally meander and sort of just spray sediment all over the place over geological time and build up the land, now because of our flood protection structures, we have to sort of manually open up some gates and push sediment out onto the marsh to help replenish the marsh. Otherwise, Louisiana will keep sinking into the Gulf, or at least parts of Louisiana will. Okay, this talk is really about a very specific aspect of this process, and that is how water and hopefully soon sediment interacts with coastal vegetation. So one of the things I'll be looking at are mangroves. So mangroves are a plant species that's evolved for coastal settings. They function well in high salinity and warm climates, and because the climate is warming, they're moving northward. So this is one issue that we have to be concerned with on top of just the sea level rising and the climate change and other human aspects. The vegetation is changing underneath us as well, and that has an interaction. So the mangroves are migrating northward. They don't tend to be able to survive under hard freezes, but as we have fewer of those, they will push out some of the salt marshes and things that we have right now, and that will affect things for better or worse, and we need to understand how that happens. Another aspect of vegetation that's important, there's been a kind of a hot topic in engineering, has been the use of nature-based features or natural features. So we want to use wetlands, floodplains, another feature called a living shoreline. So it's a natural features with vegetation, but we want to employ them for the purpose of flood protection and storm protection. So we need to predict how they perform. So understanding how vegetation performs, particularly how waves are attenuated as they transit through vegetation, is an important part of kind of using that natural feature in an engineering setting. So quantifying the attenuation. And right now, a lot of the way that's done is in physical experiments. So here's a large flume at Oregon State University where they have been studying mangroves. And the way they've been doing it is filling their test section with artificial mangroves made out of PVC pipe structures. And so you load up the flume, and then you run a range of wave conditions through it, and you look at how the waves attenuate as they pass through that. So one thing we can do computationally is maybe use the actual morphology of real vegetation by going out and doing lidar scans. The other thing we can do, of course, is study a wider range of cases. These are actually, if I remember correctly, the Oregon State experiments are actually to scale, but most places that have flumes don't have flumes large enough, so they're going to introduce scaling effects in their experiments. So here's the idea, and we were looking at this before so I don't have a nice picture with the mangroves, but we've been developing these computational tools, I and colleagues at the Corps of Engineers, for a long time, over 10 years. And so this is just a particular simulation where I've kind of zoomed in on what's called a spilling breaker. So it's a particular range of waves that instead of forming a nice curl and plunging, the tops break apart and they spill. It's very turbulent. And this is a part of how those waves are going to dissipate as they're moving inshore. So this is something that you would understand with a physical flume, and it's something that we can predict with a computational flume. So what we're trying to do is, reproduce some of that success in the context of vegetation. So here's the lidar approach. So this is a lidar scan of a mangrove forest in Florida. And I like to show this because number one, it just shows the complexity of these scans. So it's, this is where there is some similarities between the biological system of the human body being very complex morphologically and these larger, ecological systems. So we get lots of branching and overlapping between the mangrove roots. And of course, LiDAR is amazing. It picks up everything. I like how the grad students are over there in the scan. So the idea is, take this messy geometry, post-process it in some way so that we can use it computationally. And so this is just the cleaning process of extracting one mangrove system to look at. So that produces a triangulated surface. They're typically very low quality. We're typically not successful at generating boundary-conforming meshes with with standard mesh generation software. So because we had been looking at level set methods for the complex free surfaces that we have to model, we thought, well, let's start using embedded solids using level set descriptions of these vegetation structures. So that's part of the method that I'll talk about today. So we also, in what I'll show, we've also considering the PVC mangrove. So in terms of validation, that's a system that's easy enough that we can use a conforming mesh on it, but we also study it with this embedded method. So so now let me just drop down to some of the methods that I thought many of you are probably, or at least some of you are probably familiar with these methods, but I thought that you might have some interest in sort of the mechanics of the immersed and embedded methods that we're using. So I'll simplify it a little bit to just an air phase, a water phase, and a solid phase. And so we have three distinct phases. We have interfaces between those. They're all dynamic, but we have different types of jump conditions across those different interfaces. And so we need some different approaches for example, the fluid-solid interface we need to handle differently than the air-water interface. So we've got our domain omega. We've partitioned it into three subdomains, and we've got interfaces between those, and we'll need to apply different approaches. So before jumping into the Navier-Stokes systems, let me just step back to a simpler system. So I said two-phase Poisson test problem. I guess I got a little greedy and went ahead and stuck in a more general elliptic system. So this 0.1 is just my equation. It's my elliptic equation. So I'll consider a linear case first. The thing is, it has coefficients that may jump as they go between, in this case, just phase 1 and phase 0. So I have my domain omega. It's partitioned in omega 1 and omega 2. And the coefficients may jump as they go across, as they go from omega 1 to omega 2. They could be constants in either domain, or they might smoothly vary. But we want to be able to deal with this jump as they cross between materials. Then we also, in terms of boundary conditions between those two subdomains, we might have a jump in the solution variable itself. So U is my unknown, and it might jump. So in this particular case, we're thinking about things like surface tension, right? So in that case, we're going to have a jump in pressure as we move from the air phase to the water phase if we're trying to consider an interface that has surface tension. And then we might also have a condition on the flux, which in this case I've just written as the flux out of one phase has to equal the flux into the other phase. So N1 would be my normal pointing from the omega 1 phase to the omega 2 domain, and I'm just setting those two fluxes equal to each other. And then just for sort of closure, I've added a boundary condition around the exterior, so just a no flux condition. So in this case, A, B, and C, and D are independent of the solution. N is the outward normal on the physical domain, and then N1 is the outward normal, sorry, it's a typo, on boundary of omega 1. So here are the two methods that we're working on for enforcing our jump conditions on different domains. So one of them goes back to Nietzsche and is pretty widely used. I took this from I started looking at this. There's a paper by Bretzi where he's covering discontinuous Galerkin methods, and he goes through, how the origins of the penalty terms in discontinuous Galerkin are related to Nietzsche's approach. And so that's really all I'm doing here is I'm taking my, in this case, we can go ahead and drop down to the level of a cell of our discretization, so you can think of a triangle, and I'm going to enforce the physical equations on omega 1 in the cell and omega 2 in the cell. That's where I have two different sets of coefficients. And then I need to add my boundary constraints So 0.7 and 0.8 are the flux terms that would arise from integration by parts over the two subdomains. So those would cancel each other if they're equal. And then I would add a penalty. And then I think the novelty kind of associated with Nietzsche is that, you know, you can add the penalty, but and people tried to do that, but you get a better method. It's less dependent on the parameter C, which is a penalty coefficient, if you include the physical fluxes, and then you include this second term over here, which is sometimes called the adjoint consistency term. And so that, if you know, this would be a symmetric problem if we didn't have any advection. And so the adjoint consistency terms is so these are edge integrals over the internal edge or the cut. And so these terms are going to give us symmetry if the underlying problem is symmetry. So it preserves symmetry. And again, in practice, you get better behavior of these penalty type schemes, essentially optimal convergence, where C is independent of the order of the polynomials that you use in your finite element method. So so this is sort of the weak enforcement of the jumps through the Nietzsche approach, and this is often associated with a method called CutFEM. And CutFEM takes this idea, applies it over these internal cuts, and then adds some additional penalty terms that are necessary for robustness. And I'll talk about those in just a second. But this is the underlying way of how you can enforce these boundary conditions over a cut. And so some of the issues that I have with this are you're going to have to start carrying two sets of unknowns on the cut cells. Okay, so to have this representation, I have my unknown represented on each subdomain of the cell, and it's going to need degrees of freedom, if we're talking about triangles, at all the vertices of the triangle to represent that distinctly from the other phase. Okay, so, and that's kind of associated with the with this Nietzsche approach anyway, is you're letting you're not strongly enforcing the Dirichlet condition, and so you basically have an extra source of variability there. So that can be a problem if you're trying to, say, do air-water flow and you're tracking the phase interface as it's moving and breaking and all that. The cut cells are going to have to carry an extra set of degrees of freedom on each one of those cut triangles, which is going to be moving around in space. So a little bit of a pain from a computational perspective. The other thing that is, I guess that's something I've learned the hard way through trying to produce software that is used by engineers in practice, is that there really is a strong reason to develop parameter-free numerical methods. You leave the tunable parameters in there, they become a robustness issue. You know, some of the engineers, well, I'm an engineer, but you really want to set it and forget it for a lot of these parameters. You don't want to have to teach people how to tune them. So that's a problem. And then there's also this ghost penalty that's needed, and I'll come back to that. There is an alternative approach I wanted to point out, and I meant to put the author in there. So there's something called the aggregated unfitted finite element method by Santiago Badia. And you could enforce the boundary conditions this way without using the ghost cells, using his aggregation approach. And so that's one way to get around having a penalty parameter. All right, so now looking at a different approach. This is, again, my kind of hacked up version of what's known as the immersed finite element method, which was based on work from Levesque and Lee on the immersed interface method. And I like to think of it as just the strong approach, so that we're all familiar with from our finite elements, right? So the basic theory that you go through to begin with is, you're going to take your Dirichlet conditions and you're going to enforce them on the space before you go to solving them. Okay, so in this case, the idea is I have this immersed interface. It has conditions along the jumps, so I'm going to do some math to enforce them directly on my space, and then I move ahead. And so I've worked this out just for illustration for a one-dimensional problem, and I'll show you kind of what things look like in 2D. But the idea here is, instead of doubling the degrees of freedom, I'm sort of doubling my basis function. So I'm gonna build a composite, a new basis function, by allowing two completely separate piecewise linear functions, and I'm going to enforce the jump conditions on that system. So in this case, it's 1D. I'm going to use linear basis functions, so I have two parameters for my basis function, A1 and B1. But now I'm going to have two of those. So now I've got A2 and B2. So I've got four unknowns. Normally for the finite element method, where I just had two unknowns, I would just have my conditions from the Kronecker delta that one basis function should be 1 at one node and 0 at the other, and the other one vice versa. So those would be my standard conditions for finite elements. But now add my jump conditions. Okay, so this would be enforcing a jump on the basis functions as they jump, as one basis function jumps from 1 to 2, so from omega 1 to omega 2. And the other one would be that I have that the fluxes are equal for the basis functions. So now I've got four unknowns, I've got four constraints, and I can solve this. And so I believe that in Lee's book, there's a SCIFEM book on the immersed interface method. He goes through the proof that this system is solvable. I wrote up little Python scripts using SymPy, and you can solve these systems symbolically to generate these basis functions. As function, they're going to depend on the physics to some extent. It depends on the coefficients. As I've written this one right here, it also actually depends on the unknowns, which I don't really like, but I don't think, my reading of some of their work, there are some ways to enforce the jump without doing this, but it's the only way I could see to do it. So again, I write my little Python script, I enforce this solution, and I get basis functions. To explain this, the black line would be the original basis functions, our classical finite element basis function, and the new composite basis function would be, the dark red line union with the dark blue line. Okay, so I get a break in the slope of the basis function. That comes in from the fact that my coefficients have a jump discontinuity, and then I actually have a jump discontinuity in the basis functions themselves. That comes from the enforcement of that jump on the solution. And then you can do the same thing with triangles. So these, again, the new basis function are the darker parts of these. They behave at the nodes just like the old basis functions, but they have a break in the slope and potentially in the continuity. So that's all I'm going to say about those. The tricky thing about this from an implementation perspective is that you do have to have some way of doing subcell integration because of the break in continuity or the change in slopes. And I'll talk a little bit about how we do that, which is something separate. So coming back to the full system, so again, we've got solid, water, air. We have the interfaces between the fluid and the solid and between the two fluids. And we're going to use a level set approach for that. So very briefly, we have a scalar function, phi, and we use that to represent implicitly the multiphase geometry. So when we have a level set phi s, when it's less than 0, we're inside the solid. When phi s is positive, we're in a fluid. And then we have a fluid level set phi f. When it's less than 0, we're in the water. When it's greater than 0, we're in the air. And then we're going to use that implicit function or level set to enforce the boundary conditions using one of those two approaches, either the Nietzsche approach, which we implement fully with this CutFEM approach, or the immersed finite element scheme. So in the context of the Navier-Stokes equations, it looks something like kind of like this. We have a continuity equation, and then we're multiplying that by a Heaviside function, and that's the Heaviside function of the solid level set. So if phi s is less than 0, we're inside the solid, so we're not enforcing the continuity equation. When phi s is positive, it's 1, and we're in the fluid, so we have div dot v. Then we have some kinematic conditions on the solid, which I'll show in just a second. And then we have continuity of the normal component of the velocity as we go from fluid to solid. Then we have the momentum equation, same thing where it's kind of multiplied by this switch. So we're turning on the momentum when we're inside the fluid. And then we have the dynamic conditions on the solid, which will be the no-slip condition. And for our case, if we're talking about solid motion, we just set v equal to the solid phase velocity, which we model like with a rigid body code. Typically we'll use something like a discrete element method or just some simple 6 degree of freedom motion. So we're not doing elasticity like you might be doing in your cardiac modeling. We're typically talking about solid rigid particles. And so in that case, we just grab the velocity from the solid velocity and we set pressure equal to 0 inside the solid. So again, this is just what I've already showed for the Poisson equation. This is what it looks like for our momentum equation. And so we've added in terms with our viscosity. These are the adjoint consistency term, the momentum flux term, and the penalty. That has to be enforced over the interface between the fluid and the solid, which we write as the integral over the volume, multiplying that term by the Dirac function of the level set. And so this is often done using a regularized Dirac function. So I think that's sort of the method that goes back to Peskin and others. What we're not doing is regularizing the Dirac function. So I'll show that approach next after I talk about the ghost penalty. So this is the last step that you need for those schemes, which is when you apply something like the Nietzsche method over the cuts, you have these degenerate cases where the embedded interface essentially doesn't have enough physics left to stably enforce the solution. So in this case, I've just done a simple parabolic flow with no slip conditions. And if you just use the straight Nietzsche method, there are cells where the interface is so, I know you can't see it from out there, but you're so close to the edge of the end of the cell that there's essentially no support inside the domain. And you start to lose control of the behavior. So the solution looks good, but you're losing control at specific nodes, and your solvers don't like that. So the ghost penalty method that's attributed to Berman essentially adds some stabilization terms based on the jumps at the faces that are connected with cut cells. And an important thing to note from this, kind of from the perspective of PETSc and for finite element codes in general, is we're using a continuous finite element scheme for this. So our basis functions have support that we're used to. When you start adding these jump terms over edges, you're extending that support out. Essentially, so something that looks kind of like a bow tie. So if you've ever done discontinuous Galerkin methods implicitly, you've dealt with this issue because this is the same thing that happens in those cases. So your support is wider at these cut cells, which is a little bit of an irritation. But it does work well. So this is just this is with ghost penalty, without. And I'll point you to an interesting paper by Andre Massing from 2017, where he kind of goes through the theory on this for the Oseen problem. The interesting thing about his paper as well is that his entire method uses edge terms. And so in some sense, that's appealing to me. If I'm going to have that extended stencil anyway, it ought to buy me something. And his approach gets uniform optimal order for what do you call it? He's using uniform order on pressure and velocity space. So P1 for pressure, P1 for velocity. It doesn't have to use mixed elements, and he doesn't have to use internal stabilization, and he recovers second order convergence for both pressure and velocity for that scheme. So it's kind of an interesting approach. Again, particularly if you're going to be doing this anyway because of interfaces, you could use that scheme because you're going to have those extended stencils anyway. Okay. So, and I was going to try to sneak in the approach that's used on the immersed finite element method. So it also requires a type of edge stabilization, but I didn't have time to get that clearly into the slide. So from the perspective of that extended stencil, there's no winner here. They both end up having to extend the stencil out and extend the support from edge type stabilization terms. So the paper that describes those terms for the immersed finite element method is one on a scheme they called the symmetric consistent immersed finite element method, and they have a paper on that in 2014, and they've got another one out in 2022 that uses a similar scheme. Okay, so the last bit, and I'm not sure what I'm at, where I am.
Like 4 minutes.
Okay, so I'll wrap up. So the last thing is, how do you deal with these all these integrals that have to be over partial cells or over interfaces that cut through cells? If you look at the CutFEM literature, they go ahead and kind of take the bull by the horns, and they break their cells up and they integrate over them. I was working from a core, code that we developed, PETSc-based code. It was parallelized and running on very large machines. I really didn't want to go in and develop that additional infrastructure. And so I found an interesting paper by Ventura and Benvenuti where they developed this technique they call equivalent polynomials. It's very similar to an adaptive quadrature scheme that was developed by Holditch and David Noble and Secor. And they all kind of have a similar flavor, but I like the approach that Ventura took, because what it allowed me to do is go in and replace all of the regularized Heaviside and Dirac functions that we were using to do these types of subcell integrations. And those regularizations were causing us to lose an order in convergence. So we had a technically order h squared finite element scheme, but we were getting order h at all of our interfaces. And so this approach allows you to build a polynomial Heaviside and a polynomial Dirac function. And they have the property that they integrate the Dirac function and the Heaviside function exactly. Okay? And so this is how it works. You choose, what order polynomials that you're going to be using on your elements. So you can think just P1, but you can do P2. I have a code that generates these things up to like order 12 or something like that. So you write it just like you were going to be doing. Has a very similar flavor to what Mark Adams presented this morning with projections. I mean, we do these things a lot in finite elements. So we expand our function as a polynomial in a space. In this case, that's my h hat. And then I set that equal to the true thing, which is the integral of the Heaviside times a test function. And I do those exactly, but I do them symbolically as a function of the unknowns of the level set, which describes where the interface is. So I have an analytical expression for the right-hand side as a function of the degrees of freedom of the level set and the basis function that I'm interested in. So the right-hand side is analytical. The left-hand side is also analytical. Everything over there is polynomial. And so what I end up with is a mass matrix times the coefficients of my polynomial. This is going to be my Heaviside representation. And then I have an analytical right-hand side. And so what happens in the code is you're looping over the elements. Most things are not intersected by an interface. You hit something that is intersected, and that's where you have to stop, evaluate your polynomial coefficients, and then you just continue on. You use that polynomial in the place of your smooth Heaviside function. It has a nice property that you can just differentiate it with respect to the unknowns of the level set, and you get the polynomial Dirac function. So everywhere you just swap these out, and you have exact integration. The price that you pay is that now your finite element scheme, like let's say you were doing Navier-Stokes, and so you had some terms in there that were maybe cubics because you've got a quadratic term, you've got a weight function. Now you're multiplying that by a Heaviside function that's also cubic, so you've got to do 6th order quadrature in order to make that exact. Or you could do exact integration, but we do quadrature. So anyway, that's kind of the closure of our approach. I'll show you some of the results. What we're trying to do is run these numerical experiments, quantify the effect of the vegetation, and then introduce those into larger scale models. And so one important larger scale wave model is what's called fully nonlinear potential flow. In that case, the vegetation just gets pushed into that coefficient, the damping coefficient in the potential flow. Another one, you're probably familiar with the St. Bernard equations or the shallow water equations. You can extend that to deal with non-hydrostatic pressure effects, but you can then push your vegetation into drag terms. So there's a quadratic and a linear drag term. So what we'd like to do is run the full three-dimensional Navier-Stokes model, actually representing the vegetation, run a series of experiments, and then derive these coefficients for these larger scale models. So these are what some of those numerical experiments look like. So we're producing, in this case, the coefficients for a quadratic drag model. The right figure here is simply sort of a validation on what the projected area is. So that's the area perpendicular to flow as you move up from the ground through the mangrove. Okay, so this is just a representation of the fact that these mangroves, have a trunk and then they spread out and go down like that. So this is an example of kind of what the velocity fields look like. So they're, the Reynolds numbers here are not super high, but they're high enough that you're getting unsteady flows, vortex shedding and stuff like that. This is from one of the PVC mangroves. That's why it looks relatively nice. Here are some, I believe, with the true mangrove or a lidar of a mangrove. That's what it looks like. And then these are just some results where we're comparing, in this case, that Serre-Green-Nogdy St. Venant type model against wave gauges from a flume once we've fit the vegetation damping from our smaller scale experiment. So we get really nice, recovery of the transmission through those systems with our reduced models based on the coefficients that we derived. Okay, so ongoing work. I would have liked to have shown you some of some results with the immersed interface finite element scheme dealing with the air-water interface, but we hadn't quite finished that yet. But that's important because, as far as I could tell, that's the best way to be able to preserve certain important states, like just hydrostatic equilibrium, which is not preserved in some of the Nietzsche-based approach. We're working on validation on some more flume experiments from Polytechnic of Torino, which has some kind of interesting effects where the standard models of vegetation are they're essentially over-predicting how vegetation would protect you from waves. Okay, so they're going to say, okay, this field of vegetation has this characteristic diameter, and so it's going to attenuate waves like this. The Torino experiments are showing that you're going to get half that much attenuation. Okay, so that's the thing where we want to apply this to improving the reliability of our engineering. And then we really have to be working on coupling of reduced order models. I mean, these models are not feasible and probably never will be feasible for any type of realistic coastal engineering. So we have to come up with some better approaches for either multi-scale coupling or model reduction. So, and I should say Darsh is going to present tomorrow. He's got some better results or deeper results on just the PETSc side of things and the efficiency of that kind of underlying Poisson problem for some of that we're kind of, I'm in a phase of sort of retooling and rebuilding, trying to go back to some unfinished work. And so that's partly why we're dropping back to the Poisson problem. So thank you.
Yeah, please.
So maybe that's an unfair question, but when I see that, I feel the same way as sitting in an CutFEM lecture for fracture is that this is awfully complicated. Mm-hmm. And pretty much any method that involves cutting elements lead to this nightmare at the interface. Mm-hmm. And you've only looked at the easy problem, mm-hmm. as far as I understand. You've just assumed that your element is small compared to the diameter of the tube, so you can assume that local geometry is planar, so that you're only looking at the intersection of an element and a plane. Mm-hmm. But you look at highly branched and non-smooth geometry, so you also at some point have to deal with what happens when you're close to a junction between one root and a trunk, which is an absolute nightmare. And in context of fracture, it's been, it will be done tomorrow, but it's been done, we've been hearing that for 30 years. So is the idea of doing a fitted mesh method really the right thing here? Like doing a sharp interface problem versus a diffuse interface problem where you just don't care about the geometry at all.
Yeah. So let me take the last part first. I was perfectly happy with using like regularized delta functions and heaviside functions. I mean, it's really easy to write the equations and to put these things around and kind of just smooth over things. But we could never get reproduction of drag forces on solids accurately with those methods. So we're either in a situation of going back to a conforming mesh where we know how to do adaptive mesh refinement and we can recover the drag to get the forces right, or we needed to try to get, or do something to get higher accuracy there. And what gave us the higher accuracy, and there's a bunch of different ways to do it, was getting those heaviside and Dirac integrals exact, getting back optimal convergence for our finite element scheme. So that was the motivating factor, was really, in those days, I was still at the core and we were looking at floating structures. So we hit the added mass problem that David talked about. So you get instability because of added mass. And that's exacerbated when you have very low accuracy on your forces themselves. So I thought, we had to get both right before we could finally do floating structures well in wave-driven environments. Now those interfaces, those are man-made structures, so they were simpler. The other part of your question that I didn't do a very good job, I think, presenting it, and I seem to never do that, but I haven't quite figured out how to. I want to show some of the details, but I also want you to think it's easy, right? And and I don't do a very good job with that. So what is so wonderful about this scheme, which I did not invent, is that code that you write, just throwing heavisides and deltas around, it just works. You replace them with these equivalent polynomials, and they're exact. And so it's one of those things, it's the classic thing of do the hard work up front. In this case, with symbolic algebra and sort of formulations, you produce these polynomials, and then it's really not that hard. Your code is actually quite clean. It's a standard loop over the elements. It just has this thing that looks like another coefficient in it, which happens to be a polynomial, but you've constructed it in such a way that it preserves the exact integration over the cut cells.
What if you have to cut yourself twice? So if you have two planes that intersect your cut, which would be what happened if you even in
the triple point
junction.
Yeah.
And that's what stopped the fracture people.
Yeah.
I mean, they've been almost able to do that for 30
Yeah.
years.
No, there I have to just agree with you. I mean, what we do in that particular case is we drop back to the smooth heavisides functions. But it's all, sometimes nature does us a favor, right? In some case, when we pick up enough of the branching structure and the complexity of the mangrove, we start to zoom in on the correct values. The other thing, of course, is that at that triple point, there's a lot unknown about the physics itself there. And so, so I don't know, but you're right. I can't disagree with you there.
We could probably discuss it a little bit more offline. Thanks a lot, Chris.